Hey everyone, welcome to 5.4 on comparison tests. So today there's just two tests we're going to learn, direct comparison, sometimes called basic comparison. And then we'll go over the integral test. So direct comparison is just that you have two sequences. Well, you're given one sequence, and then you're asked to determine whether or not it converges or diverges. So the key here is coming up with then a second sequence. So if you suspect that your series converges, you want to find a second convergent series such that the sequence from Bn is bigger than An. Right, so the idea is you want to say, hey, look, this thing that's bigger, it converges. So my guy that's smaller, it must also converge, right? Like, how could I be smaller than it and this thing's finite? And then conversely, you want to do the same or something similar if you suspect that your series diverges. But if you suspect that your series diverges, then you'd want to find a series smaller than yours that also diverges. Okay, that's cool. Doesn't want to work. ST stands for such that. So again, here, if you suspect that your given series diverges, you want to find another series that's smaller than yours that diverges. You'd be like, look, that guy's smaller than me, but even he is divergent. So me being bigger than it, of course, I have to diverge. So that's what the direct comparison test shows. The skill in this is kind of determining, one, whether or not you think your series converges or diverges, and two, what to compare it to. So for example A, the idea here when you have polynomials is just look at the lead term. So I'm going to suspect that because my leading term is cubed, this is going to behave a lot like a p-series with p equals 3, which is convergent. So I want to compare this to a convergent p-series 1 over n cubed, right? So here the p value is 3, so I know that this converges. Because I want to show that this converges, I have to show that the thing I'm comparing it to is bigger, right? I want to say, hey, look, that guy over there is bigger than me. He's still converging. I'm smaller. I must also have to converge too. So what you want to do, so you want to show, WTS want to show that 1 over n cubed plus 3n plus 1, you want to show that it is smaller than 1 over n cubed. And this is pretty obvious, right? N is positive. So this is true because n is positive, right? So the denominator on the left is bigger than the denominator on the right. So check. Then you just conclude that your series converges, right? So I said, hey, this looks awful similar to the p-series, a convergent p-series. Not only that, it's smaller than a convergent p-series, so this thing must also converge. Notice again, we're not saying what it converges to. We're just qualifying it as convergent or non-convergent. For B, you want to look at the thing that kind of does all the work. Like 2 to the n is making everything happen. The +1, total freeloader, not doing anything, not helpful. It's not going to change whether or not it converges or diverges. The 2 to the n is what's making the denominator really large, which is going to drive the terms in the summand down to 0. So just look at two to the n, because +1 doesn't really do anything. To affect convergence or divergence. And if I'm just looking at 2 to the n, this really feels like, so 1 over 2 to the n is 1 over 2 quantity to the n. So this has strong geometric vibes. So you want to compare to this guy, which is a convergent geometric series, because r equals 1/2. So we have to manipulate this So you want to say that 1 over 2 to the n plus 1, just kidding, that plus 1 is not an exponent. We want to say that this is less than or equal to 1 over 2 to the n minus 1. And this is actually equal to 1 over 2 to the n minus 1. So if I, how do I want to do this? I'm going to multiply each side by 2 to the n plus 1. So I have 1 less than or equal to 2 to the n plus 1 over 2 to the n minus 1. Then I can split that. So I get 2 to the n over 2 to the n minus 1 plus 1 over 2 to the n minus 1. And so this simplifies to 2 plus 1 over 2 to the n minus 1. And certainly as n becomes large, this 1 over 2 to the n minus 1 guy becomes very small. But remember that the smallest this whole thing can be is 2. So we're good here. And since we showed that our sequence was term by term smaller than the sequence in the geometric series, I can conclude that 1 over 2 to the n plus 1 converges. We have one more example from this direct comparison. Which is 1 over ln 2. Okay. So the natural log is kind of a weird creature. It grows slower than linear. So ln of n is less than or equal to n, always, for all n. So what that means is that a good thing to compare this to, I'm kind of doing this in reverse order. So if ln of n is less than n, then I know that 1 over ln of n is greater than 1 over n. And this is good because 1 over n, if I compare my given series to this is a known divergent harmonic series. And again, the harmonic is just a p series with p equal to 1. So now I've shown that this is bigger than the sequence in a series that is known to be divergent. So you would conclude then that 1 over ln of n is also divergent. So next we're going to do the limit comparison test. So the limit comparison test is kind of the same idea where you get an idea for your given series, like, okay, I think this converges, I think it diverges. I want to compare it to something that's known to be convergent or divergent. And instead of doing comparing the terms in the summand, term by term, we're actually going to take the ratio of terms and then evaluate it as a limit. So if you so usually you're given an, and then you have to choose bn. So if you kind of stack an over bn and take the limit, if that limit exists and there's some finite number that's not 0, then they either both converge or both diverge. 2 and 3 are interesting. So for 2, if an over bn, if that goes to 0, then bn is outpacing an, right? So you could think of that as like an is smaller. So then if bn converges and an is smaller than it, then an has to converge too. Conversely, if an over bn goes to 0, then an is outpacing, right? It's really kind of dominating bn. So we know that an is bigger. So if an is bigger than bn and bn is divergent, then if you're bigger than something that's already diverging, then you better be diverging too. So that's kind of the justification for the limit comparison test. It's a very light, hand-wavy, intuitive justification. You can definitely read the proof in the textbook if you like. So let's do these 3 examples really quickly. So n equals 1 to infinity of 1 over the square root of n plus 1. So again, you're still looking at that first term. That plus 1 isn't doing anything for us. So you kind of want to compare this to 1 over root n. That's what we're getting at. One over root n is a divergent p series with p equals 1/2. So now I want to take the limit as n goes to infinity of 1 over n plus 1, right? So this is an. Over 1 over root n, and this is bn, right? This is the one that we chose. And so this limit is going to be one. So again, you can apply L'Hopital's rule here, but we all know that the limit is 1. So when the limit is a finite number not equal to 0, then both series converge or both series diverge. Since we know that 1 over root n is a divergent p-series, we would conclude that 1 over the square root of n plus 1 also diverges. Okay, for B, we're given this series here. And again, not doing anything useful. So just consider the parts that are actually contributing to the behavior of this series, which are really 2 to the n over 3 to the n. So this to me looks geometric, so let's compare to this geometric series, which I know converges. So I want to take the limit as n goes to infinity of 2 to the n plus 1 over 3 to the n over, I'm going to write this as 2 to the n minus 1 over 3 to the n minus 1. So this is b sub n, and this is a sub n, and this is a fraction of fractions. So to simplify this, I'm going to get 3 to the n minus 1, 3 to the n, 2 to the n minus 1, and then 2 to the n plus 1. So we get some nice cancellation here. The limit as n goes to infinity of 1 over 3 times 2 to the n plus 1 over 2 to the n minus 1. I could split this up. I think I did this just earlier. So 2 to the n over 2 to the n minus 1 becomes 2. And then the limit as this 2 to the n minus 1 and the denominator will go to 0. So this should be, I'm not even going to bother writing the next step. We'll just say, notice that this goes to 0. And then the simplification is that this just equals 2/3. So again, we have that the limit of an over bn is non-zero finite. So since the geometric series that we chose to compare it to converges, we would conclude that our given series 2 to the n plus 1 over 3 to the n also converges. And then lastly, ln n over n squared. Okay. So again, you want to think about the natural log of n being kind of similar to just a linear term. It's less than, so then if you think about this, then you would kind of get an idea that you want to compare it to the harmonic series. Right, so again, relating natural log of n to n, and then putting both of those over n squared. So now you kind of get an idea of what your comparison series should look like. This is divergent. So when I take this limit, I'm hoping to get something that's a finite non-zero. So I can also say, okay, well, by the way, this thing's also going to diverge. Or the other option is showing that A sub n over B sub n is infinite. Then that will also give me what I need. So I have ln of n over n squared over 1 over n So this will cancel to be ln of n over n. And you can use L'Hopital, you'll see the limit is 0. But this is not what we wanted, right? So again, we are comparing it to the harmonic, which is divergent. So going back up to our conditions, we either need to show that the limit was finite non-zero or that the limit was infinite. That's the only way we can compare it to a divergent. So I'm like, okay, well then the limit comparison test then doesn't apply with this choice of Bn. So you may also try, okay, so let's do round 2. So you may also try this. You might say, okay, well, ln of n, it's less than linear, but maybe it's like kind of close to like 1. So let's do n squared 1 over n squared. And so you compare it to a convergent p-series 1 over n squared. So let's try that limit. So now if I'm going to compare it to a convergent p-series, I either need to show that the limit is 0, which would be the second condition, or I need to show that the limit is finite non-zero. So let's see what we get here. So we get ln of n over n squared over 1 over n squared. And so this is just the limit as n goes to infinity of ln of n, which is infinity. So the limit comparison theorem still didn't work. So we know that 1 over n squared was a bad choice. But I know that ln is lives somewhere between like 1, the constant function 1, and the linear function n. So is there something I can choose that will, a p-value, right? Because I did both to compare them both to p-series, p equals 1 and p equals 2. Is there an in-between place that I can compare that to? And the lazy man's answer to that question is yes. Let's just take the midway point. So let's try this one more time. We still have our series ln of n over n squared, but we know that p equals 2 didn't work, and we know that p equals 1 also didn't work. That was a fail. P equals 2, that was also a fail. So let's just try p equals 1.5. So 1 over n to the 3 halves. This is convergent with p equals 3 halves, which is greater than 1. So this is a convergent p-series. And if this doesn't work, I'm just going to, I don't know, find a new job. But I'm feeling hopeful. I also looked in the book, so I'm good. ln of n over n squared over 1 over n to the 3 halves. Okay, so simplifying this, I'm going to get n to the 3 halves times ln of n over n squared. So what I get is the limit as n goes to infinity of natural log of n over root n. So this is prime for L'Hopital, infinity over infinity. So I'm going to get one over n times 1 over 2 root n. So to simplify this, I'm going to get 2 root n over n, which is 2 over the square root of n. And this is 0. And I'm like, okay, wait, now I've totally forgotten all the rules. But actually, this is good. So remember, if we're comparing it to a convergent series, and a p-series with 3 halves, that's a convergent series, it's okay to get 0. We either need a finite non-zero, that's condition 1, or we need 0. So we conclude that ln of n over n squared converges. So I kind of wanted to show you the roundabout version of that, just because ln, the natural log, is enigmatic, charming, beautiful, wonderful, sometimes hard to work with. It's okay to kind of try out different boundaries in either direction in order to find a p-value that works for you. So math is a creative process, so don't be afraid to guess incorrectly, as long as you learn from kind of where you went wrong. So that's all I've got for this section. Good luck. I'll see you soon.